Hi all, myself Mithun. I work as a database engineer in ParadeDB. I have around 17 years of experience in working in database, some around 10 years in Postgres internals and some around 7 years with MySQL and code base. I have done some contributions in both of the code bases. Today's talk is about ParadeDB's extension called PGSearch. The story is about how we are able to fit in a search engine inside the Postgres. The flow will be, we will just try to see how the current state of full text search inside the Postgres and what it is missing, and our extension PGSearch, how it is going to improve the full text search and also the aggregates and facets inside it. We have some benchmarking slides to show the improvements we were able to make over the native Postgres. I think before the talk we should be knowing some of the terms related to full text search. The first one is tokenization. Tokenization is nothing but you have text data, you are going to split it into words and then you are going to index it. Then it's stemming. Stemming is like, now you have already split the words. There could be two words which are same, like run and running, and it has to match the same results. So we just go to their root word and then we go to index it. Then inverted index is actually most common index which we use for as a search index, which gives the matching documents for your given query search term. Aggregation we already know, and the facet is an interesting thing, especially in the text search. If you do a search, generally you get list of documents, and along with that you will see small numbers around it. That's nothing but some aggregations happening there, like count, number of documents, all such things. Facet is the unique property when somebody is searching, they expect such kind of results. Next, what is ParadeDB? It's actually if somebody is using Elasticsearch for full text search along with your Postgres, we have built a search engine inside the Postgres now. It is written in Rust. There is a PGRX platform which supports Rust extension to be written for Postgres. And people who are already using Elasticsearch for their full text search, if they want to migrate for ParadeDB, there are reasons they do it, because Elasticsearch is not an transactional database. So Postgres is. If you have search engine inside Postgres, you get those functionalities, and data freshness is the issue, because whenever you have two data stores, you need to do the ETL, you need to wait for the sync to do the searching, and the schema in both the data stores will be different. Elasticsearch you need to denormalize and then start building it. And another thing is, like nowadays, like you just want to use Postgres for all the workloads. That's the reason they just want to come to ParadeDB. Let's start with the full text search. Maybe the introduction, what is exactly it is. It's just querying your documents for a particular term. It can be the queries can be very simple, like search for a particular word, or it could be very complex. You want but some words to be ranked higher, some words to be ranked lower, and you want to combine some of the searching. Much more layered search queries can be there. Internally, how the search looks is there are two concepts. One, you need to do the indexing of your tokens, which is generally an inverted index, and the next you have a query which we are going to search inside that inverted index. Currently, if you look into the state, what the Postgres have is it has a like operator, and the most functional is the TS vector, TS rank with the GIN index, and we have the PG trigram. The like operator is a simple one. It mostly goes to the sequential scan, because if you have an infix kind of search, it doesn't index. It is very limited full text search functionalities, and there is no ranking. So if you want a rank, you don't get it. So the really operational one is the TS vector for your serious use cases, and the GIN index. GIN index is actually the inverted index. So it stores TS vector is the tokenization thing which I have discussed earlier. So you tokenize your text and store your terms inside the gin index. It will point to which are the documents which are matching. And there is a TS rank. Actually, gin index doesn't support ranking within the index. So you have to come back to the heap scan and then run this TS rank function, generate the rank, and give the final result out. PG diagram is a special case. Like whenever somebody search, there will be a typos or you need autocomplete kind of facilities. So you take your term and split it into 3-character one, and all possible combination you keep it, so that if somebody made a typo, then you can do a similarity search and then you can suggest it. It's a similar concept for autocomplete. What exactly the full text search in the Postgres currently missing is the ranking. They do some sort of a term frequency kind of ranking calculation. Let me go back and tell how exactly the ranking is calculated for your searches. First, given a document, they will find out what is the frequency of the term you are searching inside the document. Next, across the documents, how unique this term is. So they give you a perspective of what should be the rank of this document when you find a term inside the document. This is good. We can currently TS rank does the TF, not the inverted document frequency. There are PG stats, TM stats kind of thing. You can also store statistics across the documents also. But problem with existing ranking is, if you have a document, it is just like a SPOM, only it has a terms, it doesn't have any meaning. Then your ranking is also going linearly, and probably when you search for such kind of terms, you get top ranked things or spawn documents only. Also, if you have a very long document, and it's natural that document can have more number of terms, but it might not add more meaning to your search. That kind of tuning TF-IDF doesn't have. The BM25, which is best match 25, it's a standardized algorithm which is since long years. Most of the search engines uses that, which is not in Postgres right now. We will go to that formula. What exactly it does is, it do the term saturation along with term frequency and IDF. If you see the graph, if the same term is repeating in the document, after certain numbers, it doesn't add to the ranks at all. The red line in the graph shows that. And if your document is unusually lengthy when compared to the average length of all the documents, and that also will not add much to the ranking. So this is more of an industry practice which currently exists for the ranking algo, which is missing in Postgres right now. So to solve that, we have an extension called PGSearch. It's actually a search engine which is inside the PostgreSQL itself now. So one database, SQL native workflow, and stronger relevance. It's built in Rust. It actually uses an full text search library called TanTV. So TanTV is very inspired by the Lucene. Both are having some similar performance at this point of time. It supports full text search and faceting also. And in the index, we can do BM25 scoring by default. It has an inverted index and also columnar index. The inverted index is used for full text search, and the columnar index is used for your faceting, aggregation, and filtering, range filtering. So it's more of a covering index. If you have a full text search, it need to do search in the documents, and you need to also do the faceting along with that, which I explain what is faceting. You can do it in a single query now and single index scan. So to fit this TanTV index inside the Postgres, PGSearch is a bridge. So what it has done is, it has built a custom index called BM25, and it has its own full text operator. So this full text operators can actually be transformed into the scans into this index, And there is a query builder because full text, TANTV itself is an engine, it has its own language. So these operators and filters need to be transformed into the TANTV language. So we have a query builder which does that. And TANTV has different indexes. We can scan it in a different ways. One is a base scan, which is your full text scan, and there is a columnar scan because we have a columnar index. And actually we can push even entire top query inside the TANTV and aggregates inside the TANTV. So it's a covering index, enables most of the operators of your query to be pushed directly into the index. The idea is push as much into the index and then minimize the heap access. So how we have built this BM25 index is, it's actually built over the Postgres block storage. So now you have everything, vol log, MVCC, integrates normally with Postgres lifecycle, all the operations you can do, backup and recovery, vacuum. As I told, it combines both inverted index and the columnar fast fields, which enables all sort of operations in your query tree, search, filtering, sorting, aggregations on the index. And mainly we want to do everything inside the index and minimize the heap access. So there we gain actually the performance. This is our syntax, regular syntax to build any index. If you see, there are, first you can see a big block. This is a full text field, and this will this is actually tokenized. This will become an inverted index, and rest of the columns will be rest of the fields become a columnar index. And the layout of our index, which is stored in a Postgres block storage, is as such. We have a metadata related to the index, which gives the index information and some amount of internal segment storage information. Each of the segment is itself an index. So here the terms and posting blocks create an inverted index where we go and do a full text search, and the fast fields is nothing but the columnar index. Field norms add some data for calculating the ranking inside the index. In fact, the posting lists have the turn frequency inside the index. So whenever you get the search results out of this index, you also get the ranking calculated there itself. So these segments are actually immutable. Whenever you write, you create one segment. We don't want to have large number of segments and want to be searching across large number of segments. So we have built an LSM tree over that. So there is a constantly at certain threshold, each layer we keep on compacting it. Also we have, whenever you write, we don't want an immutable segment to be created, a large one. So what we do is, to improve the write performance, we have an mutable segment. It is a simple buffer list of CTIDs. On the fly, you can always create a searchable immutable segment of that. When certain threshold is created, a large amount of immutable segment has appeared, then we'll just flush it and make it from mutable to immutable segment. Also, this merging, we don't want to interfere with our write operations. So we have a background worker of Postgres, which will keep on triggering and merging these immutable segments into larger segments. It's just a CTI buffers. So now we have seen like how an index is built, and there is how the write operations are happening at the very top level. Now the connection part, how to go and query this index. So let's start with a base scan. Like you have a simple text query filter. In this, as per this operator, we are just searching either wireless or Bluetooth in any of the documents. So what we do is, in the PG search, we generate a TANTV query for that, which is little more descriptive with a lot of metadata with that. This query will go and fetch the relevant documents from the inverted index along with the rank if it is asked. So the custom score enables, by default, the BM25 ranks are available with your matching documents. And we get an iterator, and over this iterator, we can just keep on fetching the next documents. This is a scan flow. There is another flow called aggregate flow. We can actually push down the aggregate node itself down because we have a columnar index. We can do the batch processing and vectorize operations now. Per segment, we again go whatever the matching documents we got it from the inverted index. We do an MVCC filter, like since now it's an ACID property database, we don't want to see the deleted records. So we have the MVCC check, which are all passes through the MVCC check. Then we do the partial aggregate in the segment, and at the end we will merge all the segments aggregates into one aggregate and then return back. I don't have the numbers here, but in our own test we were able to be 4 times faster than the regular aggregates in the Postgres because of this batch processing available. This is a bread and butter queries, top K in a search engine. Top documents limit 10 ordered by the score. So we did one small experiment for this talk. Like we wanted to thrash the shade buffers. The idea is Postgres right now compute the ranks after only going to the heap, not in the index only. So if I put all the terms across all the documents, a small set of terms, then all of them, almost all of the rows in the heap has to be fetched to compute the rank. But if it is actually done in the index, we should be escaping that. So when I did that, you can see that the latency in the Postgres FTS top N is like very fluctuating, very high. But if you see the Elastic and ParadeDB is almost stable. The second slide is for just adding some filter, probably because of bitmap scan, like Postgres, little bit better performance because number of heaps can reduce there. How we were able to do this is because of the top K scan. It's little bit of optimistic way of doing. So again, we go to each segment. The inverted index gives a set of documents which are matching. Then in the locally per segment, we have a local heap for top K. We keep filling there. Once that heap is full, we have some information now, like not all documents can enter it unless it has a rank which is higher than what all of minimum of it. So that information is fed back to the inverted index. In inverted index posting list, per blocks we have an information what is the maximum possible ranks coming from the whole block. That's a metadata kept there. So using that, the inverted index can skip a lot of the blocks. If these rankings are not coming from these group of documents, we're never going to scan them. So then all of them is coming back to only the thing which can actually enter into the top K heap is going to get into the going through the flow. And at the end, we are going to do the MVCC check. If you have a limit 10, only 10 documents MVCC check will be done. Suppose it fails there, we will increase the buffer size of the heap and then retry it. So at the end, all the per each segment's top K which are visible will be merged into global top K and return. So this has significantly reduced heap checks. In fact, we are not going to heap for calculating any of the ranks. Just for the MVCC check, we are going there. If you disable the MVCC check, the performance will go even further. I can show you in the next slide. We are doing top K facet. This is on a data set, 46 million records on Hacker News post. If you want to do the top K and facets probably in a manual way, okay, first get all the match relevant documents, then calculate the top K, and on these matching documents again do the aggregate operations and then do the join. This is like complicated flow of queries. If in our case we can actually insert this faceting aggregation in the search queries itself. I'll show how it can be done. But before that, we can see that the scaling as the number of documents being increases from the search results, the scaling in the Postgres is like not at all happening. But if you see in our case, it is nearly like 14 times faster than native Postgres full text search. If we do the MVCC off, it is going even much more higher. why this has happened, okay, before that let us see the syntax of that. Like I explained that if you want to do the top k plus facet in a single query, it is a sequence of queries you have to do. But in our thing, is a query is very simple. Like we have a pdb.aggregate function. You can just put your faceting query inside that. It will be pushed down to the TANTV query, and both of them can be search and aggregations can be done together. So previously we saw top k pipeline and we saw the aggregate pipeline. So in our case, what happens, we first go to the inverted index, collect the documents, and same documents can be iterated by both of it. Both the aggregation can also be doing that, top k can also be doing that, and later they can be merged, and then you get the results. So you got the performance enhancement done by the top k algorithm, and the aggregations both got it combined. So the theory is here, inverted index handles all the searching and ranking by itself. Columnar fast fails do the filters, sorting, grouping, and aggregation. So this whole BM25 index maximizes the push down of all the text queries, text search queries into the index, and try to minimize as much as heap, which has helped us to scale in a vertical fashion. Earlier, I think I discussed about DSL domain specific languages, which is not currently inside the Postgres. You cannot handle now. So we have a special operator. Like if you have a DSL kind of query, you can use @ operator. On the right side, you have some utility functions which will take those DSL kind of queries and convert it into a TANTV query. You can write all the complex logic you are currently using in your Elasticsearch and put it down directly here. You need not to do this stitching of your SQL. These operators work for you. And also you have, you can, like one of the important thing is how to manipulate the rankings of the searching. Elasticsearch has that. You can actually boost the ranking. You can assign some ranking. You can do some complicated calculations. We have special utility functions for that, which like PDB boost. You can actually increase the search results by 2. You can assign the ranking. PDB score is for actually whatever the ranking actually given by the inverted index. Okay, I think I was very quick here. Generally, the whole concept is we want to push as much of the search queries inside the search engine and minimize the heap, but we'll still want to be an ACID compliant database. That we were able to achieve with our extension.